Okay, let's have a look at this problem. In the probability space, consisting of the interval minus half equipped with the Borel sigma field and Lebesgue measure, let's compute the expected value of x given g, where x is a random variable defined as x squared, and g is a sigma field, which consists of all the Borel sets, all the Borel subsets of minus half, such that those sets are symmetric around 0. Now, if we want to find the conditional expectation, we need to look at the two properties of conditional expectation. The first property is that conditional expectation is expectation of x given g is g measurable. That's the first condition. And the second condition is that for all events in the sigma field, we must have that the expected value of x times the indicator function of a is equal to the expected value of the conditional expectation multiplied by the indicator function of a. And of course this is equivalent to saying that the integral over a of x with respect to my Borel measure is equal to the integral over a of expected value of x conditional on g and the Borel measure. So, what we need to do is we need to find a random variable that satisfies these two properties, and as soon as we find such a random variable, then we know that we found the conditional expectation, because these two properties define conditional expectation uniquely, almost surely. So, let's have a look. First of all, if we look at condition A, this conditional expectation must be g measurable. Now if we look at our sigma field g, then you will see this is a collection of all the Borel subsets of the interval minus half, such that these Borel sets, that these events are symmetric around 0. So a is equal to minus a means that if you look at a from the direction of 0 in either direction, then you get exactly the same picture. Now we know from experience in this module that the kind of random variables that are measurable with respect to such a sigma field tend to have the same symmetry properties as the sigma field itself. So in this case, my guess is the random variables that are measurable with respect to g are actually symmetric around 0 as well, and this is called even. This property is called evenness. Now if we look at x itself, then you will see that x is x squared. So if you apply x to the variable minus x, then you get minus x instead of x squared, and the minus cancels out. So in fact x itself, it's even. So my guess here is that the expected value of x conditional on g is just x itself. This clearly satisfies, if x is g measurable, then this satisfies the first property, and of course the second property is automatic, because if you substitute x equals to expected value of x conditional on g on the right hand side, then these equalities are trivially true. So all we need to do is we need to answer the question, is x g measurable? So to prove this, let's have a look at any Borel set B. So I'm going to prove it over here. So let's pick any Borel set B, and we look at the collection of scenarios for which x is an element of B. So this is shorthand notation for saying x an element of minus a half, such that x of x is in B. Right. Now we already know x of x is equal to x squared. So in fact x squared is also equal to x applied to minus x. So we can write this set is equal to all the x in the interval minus a half, such that x of minus x is inside my set B. Now what you can now do is you can say, okay, I'm interested in x inside this interval, so let me make this transformation from x to minus x here. So I have x to minus x, and of course these are the elements in my set, so if I make this transformation from x to minus x in here, all I need to do is to cancel out the transformation again. So let me write this down and see what we get. And what we can now do to make life easy for ourselves is we can just, instead of minus x, introduce a new random variable, z. Z is equal to minus x, and then we get z in the interval minus a half, and x applied to the random variable, x applied to the variable, it's not random, sorry, x applied to the variable z is then in B, but this looks really familiar. This is just the long form of the set x element of B, and don't forget the minus. So in other words, the set x in B is symmetric, so it already satisfies that second property. Now the question is it a Borel set? No, this is a Borel set. The reason why it's a Borel set is because x is continuous, and we know that continuous functions are Borel measurable. So x in B is in the Borel sigma field minus a half, because x is continuous. Hence, Borel measurable. So we have the property that x in B is in the Borel sigma field, x in B is symmetric around 0, therefore x in B is an element of our sigma field G, and therefore x is G measurable. And the reason why we were looking at this is because we were computing expected value of x given G, and if G is measurable, then it satisfies property A. If x is G measurable, then it satisfies property A, and therefore conditional expectation of x given G is equal to x.